Okay, so welcome to this public panel discussion on nuclear fusion for a decarbonized future. This event is co-organized by the Falling Walls Foundation and the Embassy of Italy in Berlin. Both organizers believe that open access to scientific research and also public engagement in this scientific debate are extraordinary opportunities for societal growth, and that the big challenges that our humanity is facing can only be approached by multinational collaborative efforts. So now the connection between energy production and climate is nowadays clearly recognized, and these two problems go hand in hand, and they are of planetary importance, and therefore we need a global approach and global solutions. So we know that nuclear fusion may provide, together with other clean energy sources, a long-term solution for this urgent problem. And this is what we're here to discuss today with our 5 eminent speakers. And we're very grateful that they came all the way here. They are not only, experts in the field, but they're also leading some of the major nuclear fusion centers in the world. And they come from 3 continents. So I will start by introducing them in the order in which they will speak. First of all, we have here on my left, PIETRO BARABASCHI, who is the Director General of ITER in Caradash, France. Then we have MASAYA HANADA, the Director General of Naka Fusion Institute in Japan. We then have Stephen COWLEY, Director of Princeton Plasma Physics Lab in the US. PIERGIORGio SONATO, who is the President of RFX Consortium in Padova, Italy. And finally, HARTMUT ZOHM, who is the Director at MPI, Max Planck Institute of Plasma Physics in Munich. Now, so before diving into this panel discussion, I would like to leave the word to the Deputy Head of Mission of the Italian Embassy in Berlin, Luigi Estero, who will say a few words of welcome.
Thank you very much, Professor Pascarelli, and thank you everybody for being here. I'm very happy to participate to this very interesting and important event. We will know all about the nuclear fusion. Is a very important subject, especially because nuclear fusion will be pivotal in the future for the clean energy our next generation will need. Why we are sustaining and co-organizing this event? Because, of course, as Italian Embassy, we strongly believe in the international cooperation. It is of paramount importance in the scientific research, but in all our other aspects of our life. The international cooperation, of course, starting with the one between Italy and Germany. Italy and Germany cooperate in very different fields in the scientific research, also contributing together to the ITER project, but also with their own national project. The presence of the Italian scientific research in Germany is very significant. We have more than 300 professors, university professors of Italian origin, Italian background, and more than 4,000 researchers of Italian background working in Germany. So it's a very alive, a very important interaction that we have. But of course, today we will also hear experiences and the cooperation with Japan and with United States. So this will be very, very interesting and important. It is important, the cooperation between academia and industry, especially for manufacturing countries like Germany and Italy are. So the finding innovative solution that just through an academic research can go ahead is of paramount importance also for the economic growth. And of course, it is also important the engagement in the scientific research as an element of contribution to the social growth, the social awareness. Professor Pascarelli also cited the subject, the theme of climate change. It is something that we are confronted all together, and we have to find solutions. So there is also a strong social and human, I would say, responsibility in identifying new solutions for the future. And of course, we have to look primarily towards scientific research as a guide to find this solution. So I would like to thank you so much for your presence and enjoy this very interesting journey into the nuclear fusion. Thank you so much.
Thank you very much, Dr. Estero. So now I'll say a few, let's say, technical details. So we're going to try and keep the timing. So each speaker has 10 minutes, and I will, make a sign after 7 minutes, so you know that the time is coming to the end. We want to keep at least 30 minutes at the end for questions and answers. Also, when you ask your question, please use the microphone. You will be given a microphone because this event is streamed, and otherwise nobody will hear what you say, except for the people here in the room. So this is a very diverse audience. I see there's kids, so not all of you are experts in nuclear fusion. So we decided to start with an opening video that tells you about, the physics of fusion. How does it work? What are the technological challenges that we are going into and that we have to solve? And so now we can start with this opening video.
Hydrogen as isotopes are deuterium with 1 proton and 1 neutron, and tritium with 1 proton and 2 neutrons. So they collide with a very high energy and temperature around 150 million degrees, which is 10 times higher temperature than in the center of the sun. And they can fuse, so we have helium element and we have 1 neutron. So this is the most important part of the reaction because neutron takes 80% of all energy of the fusion reaction.
Over the development of the past decades, 2 concepts have basically survived this Darwinistic process, and that's the tokamak and the stellarator. And both have in common that the magnetic field is ring-shaped. But there are subtle differences between tokamak and stellarator, not just the name.
Now, tokamak is a Russian word, and essentially it just means a donut. That is not exactly what Russian for donut is, but a tokamak is essentially a donut-shaped chamber.
So a tokamak is a Russian acronym, and means just in Russian language toroidal chamber and magnets. So it's very, very straightforward, and so it has nothing to do with the tomahawk. Never confuse that.
It turns out we need strong magnetic fields.
So we actually need 2 types of magnetic field. The first one happens in what we call the toroidal direction. This is following the shape of the torus around. But that wouldn't be quite enough to keep it completely confined. So what we do is we actually want a magnetic field as well in what we call the poloidal direction. And that sort of introduces a twist.
First thing you do is you evacuate that vacuum vessel. You pump it and you get rid of all the gas in it.
Then we're starting to charge our magnetic system around the vacuum chamber.
You put a tiny amount, about a postage stamp worth of fuel. You inject that in multiple areas.
And then you switch on a solenoid, which is in the middle of the tokamak. And this by the magic of physics, create an electric field in the donut.
The hydrogen gas, deuterium and tritium start swirling around inside the tokamak. Then our first heating system kicks on and it zaps this gas into a plasma and the whole thing starts swirling around the tokamak.
So then you use the RF heating systems and another heating system called neutral beam. You fire in beams of particles and that gets you from the sort of 1 to 10 million degrees up to the 100, 150 million degrees.
And then the process of fusion starts. The particle can knock each other sufficiently fast so they fuse, and then they produce energy. Then you have lit a sun inside your cage.
Okay, so now that everybody is on the same page, I think we are ready to start. So we now start with Pietro BARABASCHI, our first speaker, Director General of ITER. Go ahead, Pietro. And this is...
Thank you so much. So I've seen already some nice images from the previous video that we are indicating how ITER looks like with some explanation. So I will naturally not speak about the process of fusion. I will just tell you a few words and show you some images about where the ITER project stands. ITER project is really an international project. The I in ITER stands for international. It is international to the 7th power because we have 7 members that participate, more than half of the world population. And I think it's part of the objective of this beautiful scientific project is also to show that world population can work in peace for science, for a common goal. I think we should be proud of that. So the ITER project is being built now in Cadarache. It has been going on for quite some time, and I will show you some images. Is it this one? Yes. The mission of ITER is to reproduce, as was said, the nuclear fusion reaction with deuterium and tritium. I should say that it's not exactly what goes on the Sun. The Sun has a different type of reaction. It's a proton-proton reaction, which is a reactivity which is significantly lower. It wouldn't really be very practical to have proton-proton reaction on Earth, so we use deuterium and tritium because the power density is sufficiently high. Believe it or not, in the Sun, the power density is in fact closer to the one that we have in the center of our body. It gets really hot because it's so big, but it wouldn't be very practical on Earth. Besides, it would be very complicated to reproduce. So the objective is to get a thermonuclear plasma built by tritium and deuterium going. It will run for sufficiently long durations, not really in steady state, but for several minutes, which is what we think will be enough to demonstrate the technological feasibility, of course the scientific feasibility. But the technological feasibility is what has really driven the design of ITER in order to have then a future, a potential future in energy production. So we are now pretty well ahead with the construction of most of the civil works and the support systems. And you see an overview of the overall ITER site in the south of France. I will not go through each system. We don't have the time to do that, but of course you will be able to see a lot of information in the ITER website, and there are plenty of information available in the web. I will just show you a few parts. This is a view of the assembly hall, where you see segments of the vacuum vessel and coils that are pre-assembled. After pre-assembly, they will be lowered in the pit, in the big cylindrical cryostat that is, let's say, nearby the assembly hall. But this is pretty much what you would see now in the assembly hall of ITER. There is a movie here, which I would like to ask somebody to start, where I will try to describe as we fly. It's made with a drone. We start again with the assembly hall, and this huge TF coils, the D-shaped coils that create the toroidal component of the magnetic field that a colleague explained before, inside the vacuum chamber. This is, again, it's a slice of the big vacuum chamber. And this is a piece of the central solenoid. Central solenoid is the magnet that gets the plasma current started. There is a stack-up of this central solenoid. All magnets are superconducting. And superconducting requires a temperature of minus 269 Kelvin. So we have 150 million degrees in the plasma. But neighboring, we have magnets that need to be close to 4 Kelvin. And this is the cryoplant. This is the system that allows to cool the magnet to that temperature. It provides about 75 kilowatt of cooling power at 4 Kelvin. But we also have a heat rejection system because the nuclear reaction will produce about 500 megawatt of fusion power. And so there is a system which is designed to absorb this power and reject it into the atmosphere. We will not produce electricity in ITER because it's an experiment, but still we will have to exhaust this power. This is a factory in the ITER site to fabricate the biggest magnets, which are the ring coils that produce the poloidal field. They cannot be transported. They are just too big. So they had to be fabricated exactly on the ITER site, which was in itself a big challenge. All of them, again, are going to be superconducting sometimes in the close future. We move ahead and we'll show you additional parts of the ITER site. Here, you will see here how construction is ongoing for the fabrication of the building that will host the neutral beam injection system. This is going on exactly now. Neutral beam that we will hear a few words later from Piergiorgio will contribute to the heating of the plasma. And now just dive in and you will see as we enter the tokamak hall and the pit. And in the pit you see there one sector already mounted. And I should say now that we had to pull this sector out because we had to repair it. I will spend a few words about that because not everything went as planned, and in big projects I think sometimes go astray. I think we shouldn't be, too concerned about that because this is normal. I worked myself in other projects and I never had a project that everything was smooth, so we just have to get on with fixing the problem. I will tell you about that because I think it's important to be totally transparent also about problems, also make sure that others will not make the same mistake. So this again, it's an image of the TF coil, one TF coil. Each one weighs about 400 tons, and just to give you the scale, is about 17 meters high. And the cryoplant, I said before, 75 kilowatt at 4 Kelvin. It doesn't look a lot, but bear in mind that to extract energy at that temperature and exhaust it in the atmospheric, at room temperature, it takes about 1,000 times more energy. So the cryoplant is in the range of 100 megawatts necessary for the compressors. And we had some troubles now to fix. One in the vacuum vessel. Vacuum vessel had some non-conformities. We are fixing that. It's not a big trouble. And we also have found some, last year, some leaks in some helium pipes that cover the thermal shield. So bear in mind that vacuum vessel operates at about 200 centigrade.
7 minutes.
And we have also thermal shield next to the magnet, because the magnet has to be at 4 Kelvin. So we need a special shield that has to be cooled at 80 Kelvin. And so we had some cooling pipes, and one of them we found was leaking. And we found why it was leaking. And it was leaking because of a phenomena called stress corrosion. We found some residual of hydrochloric acid. And this thing happened, unfortunately. And as we found that, we decided that we wanted to fix and replace all of the pipes because we found one leak. And the reason for this is that we didn't want these pipes to leak maybe in 10 years from now. And we wanted the machine to operate for the decades to come. So taking this very seriously, but it will take us another year to replace all these cooling pipes, but we will then move on. So we are also in the process now of preparing a new baseline. A new baseline means a new plan with a new cost estimate, new planning. And so I'm not able now to tell you when we will get, our next milestones, because I will have to explain this in the middle of next year to the governance of ITER, the so-called ITER Council. But this is the big job that we are doing now. 1 minute I would like to spend on how ITER is contributing to the World Fusion Research Program. I mean, fusion is an innovation program. It's not just one project. One project can sustain much of the answers or the questions that are brought forward. But we need, and I think I welcome very much the fact that we see now a renaissance of fusion around the world, a lot of private investment interest, a lot of companies, a lot of opportunities for young people like you to work in nuclear fusion, not just in ITER, but in other instances. And I think this is very much appreciated because a lot of new ideas will come up. And I believe that ITER can provide some support also. That's why we are explaining also things that go wrong, because I think others may learn from what we are doing. It's part of our job, I believe. We will provide certainly a support to all the private investments, and the firms very much welcome around the world. I mentioned here a few, but there are literally now almost 100 around the world, small investment and larger investment companies that are addressing the problem of nuclear fusion in a different scale, in a different niche. So with this, I conclude my presentation in time, I hope.
Perfect.
Okay, perfect.
Thank you, Pietro. So thanks a lot. So as I mentioned, we keep the questions for the end. And I would like to underline something that Pietro just said, that it's great to see so many young faces here. And this is really the future. And we need you. So we need you to get excited about this. Because this is, it's your future. It's nice to see that there are many young, possibly scientists here, or engineers. Okay, we go now to our next speaker, Masaya Hanada. He's Director General of Naka Fusion Institute in Japan.
Okay, first of all, I'd like to say I'm very much honored to be invited by this meeting. So I greatly appreciate the Italian embassy. Thank you very much. So in Japan, tokamak plasma is developed in QST, National Institute for Quantum Science and Technology. We have two institutes. One is the Naka site, and the other is Rokka site. So we have totally 600 staffs employed.
Green.
Okay. So here we have the development the stage for fusion energies. We use the staged approach. We started the fusion energy since 1985. So here you can middle side you can see we are here. So we use the ITER project and also broad approach activities, which is also international collaborations. So we using the two path. We realize the demo reactor in the middle of this centuries. Here, Japanese fusion energy innovation strategies. In this April, Japanese government formulates the Japanese fusion energy innovation strategies. So Japan will not miss the opportunity to enter the burgeoning global fusion supply chain competitions. So for development of fusion industry, matching of the companies by establish of Fusion Industry Council of Japan aiming at the fusion fiscal year 2023. So second, Japan will accelerate the realization of the fusion energy. For fusion energy technologies, acceleration of the R&D, anticipating the future development of the demo through the inner ITER and broad approach. Japan will establish the fusion industry councils, strengthen its support to emerging technologies, develop educational programs. So for framework to promote the fusion energy innovation strategies, establishment of the fusion technology innovation hub, and also fusion energy education program will be provided. Here you can see the fusion technology innovation hub. This is to open innovation for the developing fusion industries. Second objective is to accelerate the demo development, fostering young leaders who are able to take initiative in the ITER and JT60SA research and in the overall integration of fusion plant towards a demo. So in both Naka and Rokkasho Institute, existing facilities are opened to fusion development to be done by industries. We have already opened the website to push the company to participate in the fusion development. Some of the Japanese companies are interested and asked to QST. So here you can see the fusion startup, also startups from the fusion development. From the viewpoint of the industrial application of the fusion technology, some of the fusion technology are to be commercialized. The defining technology of the beryllium and lithium that are used in the blanket is applied to the product, lithium and beryllium, that are widely used in the market. Startup companies are newly established as QST ventures. So we have two startup companies, Miresso and Listi. So Miresso provides the low energy consumption process of the beryllium with alkali and RF power. This also can be applied to the recycling of the rare metal. Listi provides a very simple process on lithium with the lithium ionic conductors. So I changed a little bit to change my topics. I will show the fusion development of the tokamak plasma in QST. Here we started the development in 1985. Since that, we optimize the shape of the plasma and also optimize the magnetic field. We achieved the very great record. For example, the ion temperature is 5.2 billion, not 100 million degrees, which is a Guinness record. Unfortunately, the obtained data is almost less than 100 seconds. So therefore, we decided to extend the pulse durations. One of the key issue is the heat load of the confinement magnets. So therefore, we use the superconducting magnet that is almost no resistivity. So here you can see the JT60SA right side. So this is the largest superconducting tokamak device before the ITER. So we have three objectives. One is the supportive research for ITER. Second is a complementary research for demo. So third is a foster next generations to realize the demo in the middle of this centuries. Oh. Here you can see the center side. This is the JT60SA. Very much complicated, but this is actual pictures. So we started the assembly since 2013. Then March 2020 compression of the JT60SA construction. So November 2020, coil is in superconducting state. Right side you can see the coil voltage equivalent to the resistor of the coil steeply decreased to the zero. So March 2021, integrated commissioning suspended due to the incident as a terminal joint with insufficient voltage insulating capabilities. We suspended the integrated commissioning. After that, this year, May, so we restart the integrated commissioning. So after the careful reinforcement of the insulation capability in over 100 locations. So then the July coils again in the superconducting state. So very much recently, October, we succeeded in the first plasma of the JT60 SA. So this is the big milestone to proceed our experiment. I'm very much happy to inform this good news to you.
We are too.
So
thank you.
That's all. But one say I have a time.
Yes, yes.
Okay.
You still have 2
so
minutes.
our the collaboration, broad approach, and JT60 SA is a broad approach, but strongly related with the ITER. Once we have find some the incident or something, so this information is shared with the ITER. So ITER to avoid the ITER not to same things. Okay, so right now we are in the good collaboration. Then the ITER and the JT60 SA, both of these machines, realize the next tokamak device. That's all. Thank you very much.
Thank you. Thank you very much, Masaya. I just want to point out that this is a second example. You see, when something happens, a little incident, these are such complex structures, such big structures, that they stop for 2 years. I mean, and this is just normal. So these are things that take time. It's just so that the public understands how complicated they are. Let's now go to the third speaker, Stephen Cowley, Director of Princeton Plasma Physics Lab from the US.
So I'm delightful to be here and with my colleagues in fusion. I'm going to talk a little bit about the strategy that the US has to get to fusion electricity. Because I give a lot of public talks about fusion. And at the end of every talk, somebody asks me, okay, so when are we going to have fusion electricity, right? And usually I look embarrassed. Because in fact, we've got a lot of innovation that's needed to get to fusion electricity. And up until recently, governments, the US government has had a strategy that we'll do the science of fusion. We'll figure out all the things about fusion, but we'll have no strategy for delivering electricity. But 2 things have changed that. And this last year, we had a sea change in the US government's approach to fusion. And we had, I'll get to the 2 things in a moment, I haven't forgotten them, yeah. We had a summit event in the White House, and prior to that summit, members of the Office of Science and Technology Policy from the White House and members of the Department of Energy came to Princeton to discuss how fast could we get fusion? How quickly could we get to some electricity from fusion? We had had a National Academy report that said that by the end of the 2030s or the beginning of the 2040s, the US should have an ambition to get some electricity from fusion. This was a report that completely changed the tone of the discussion. Up to that point, we had said, well, we want to do some fusion, but we'll do it as a scientific experiment, not as a preliminary to a commercial object. And this summit in the White House on March 2020, I'm the guy without the blue hair in the middle there. And on the right is actually the Secretary of Energy is in the green right in the middle of that. And these are the people very much in charge of this area of science in the United States. And they were all there, and Congress people were there. And this was to launch this bold decadal strategy for fusion. It said that the Department of Energy and the private sector should produce net electricity in a fusion plant in the United States in the 2035-2040 timeframe. Now, this is a stretch goal, because we haven't done everything in fusion. And in fact, the ITER experiment is going to be the most critical scientific step in getting to fusion. We need to actually demonstrate that you can have a self-sustained fusion burn. That's where fusion is making heat, and that heat is sustaining the plasma at a temperature like 150, 200 million degrees. And you can do that in a sustained way for some time. Until we've done that, we don't actually have the scientific demonstration that we have fusion. But what this government initiative said is we should be developing everything else simultaneously. So when we get this fusion burn, we're ready to kind of start the process of making some electricity from it immediately. So why the hurry? I mean, it's a good question, you know, after all these years of working on fusion, why are we in a hurry to do this? Well, I think the first is that energy analysis of the US energy needs, if we want to get to zero carbon in the United States, the missing link is really what we call firm energy sources. Ones that you can turn on and turn off when you need them. So that when the sun doesn't shine and we don't have solar, and when the wind doesn't blow and we don't have wind, right, we can turn on these firm energy plants and deliver from that. And the options for that are very, very few. And we need some more options in that space if we're going to decarbonize the American grid. So the first reason for this change of strategy is the need. We really do need fusion. We don't just, it's not just nice to have, but by the middle of this century, we need fusion. The second is that there have been demonstrations that make us believe that fusion is possible. And the first of this was in Princeton in 1994. We demonstrated that the green the blip on the right-hand side, it's time along the bottom, it's fusion power up the side. This machine that you can see in this picture took the temperature of a mixture of deuterium and tritium up to about 250 million degrees, and for 1 second we got 10 million watts of fusion power. I mean, this is a historic experiment, and it put fusion really on the map. It said we could get the conditions for fusion, not self-sustained fusion, but we could get the conditions for fusion. And so we could actually create those conditions that you need in a future fusion reactor. That record was broken by the Joint European Torus, which is just south of Oxford in England, and it's the European machine that was actually a little more powerful than the American machine, and that they got up to 16 million watts. That's the blue line. And that was a marvelous achievement, but one of the things, if you look at that blue line right at the end, it just collapses, right? That was not what you would call a nicely sustained conditions for fusion. At that time, the best really sustained conditions was the red line, which is 4.5 million watts of fusion power, sustained throughout the time that we could sustain the plasma, the deuterium and tritium, the fusion fuel, through that time. And that was an amazing achievement at that time. And I think it really made us confident that if we go forward to ITER, we would actually get fusion, sustained fusion burnout of ITER. And this was just the December the 21st, 2021, recently, JET broke its own record. Here they sustained essentially 10 million watts of fusion power for 5 seconds. That's as long as they could do it in that experiment. And it was a real confirmation that we can get the conditions of fusion, and this is scientifically possible. So the second reason that there's confidence and people are saying we should accelerate towards electricity and fusion is that we know we can do it. We don't know that we can sustain a fusion burn, but we know we can get the conditions. So there's some optimism that we can really get there at that time. So I see those as the two factors. And then a real shot in the arm for the American fusion program is there's another way to do fusion, and that is to make a tiny little pellet explode with fusion power by compressing it with lasers. You take the world's most powerful laser, which delivers 2 megajoules of laser light. I always think of a megajoule as about the energy of a hand grenade or a candy bar. Hand grenades release their energy faster. You take these 2 megajoules of laser light and you focus it down onto this object and you squeeze the fusion fuel down and you create fusion conditions for a nanosecond. And it explodes with fusion power. And in this case, on December the 5th, 2022, it gave more fusion power than we were putting in. And that's the first time in any experiment that we actually got into that condition where we get actually a fusion burn in the middle of this. Now, this may be a harder way actually to make fusion electricity, but it gives us some confidence. It may or may not be actually, but it gives us some confidence that we can sort of push this forward. The other big driver in the United States is that there's a huge investment in venture capital in fusion startup companies. $5 to $6 billion in investment in the last 5 years. That's phenomenal amounts in a technology that is really at a very low... I was going to say, if there's 8 minutes left, I'm really doing well. Give me 8 more minutes. One of those companies, a spin out of MIT, that's basically trying to do a high field version of ITER, high magnetic field version of ITER, has raised actually $2.2 billion in venture capital investment from people like Bill Gates and George Soros. And I quip these days that if you're a high net worth individual, you have to have a space company and a fusion company. So this is energizing the field in a big way. And some of these companies, frankly, are bonkers. Their technology will never work. And some of them are doing really, really interesting things. And I think we can see an acceleration in all the things that will drive us towards fusion electricity over this time. I want to emphasize something that perhaps doesn't get emphasized enough. Because over the last 20 years, we began to have computational models of what goes on inside a fusion experiment that actually agree with the experiment. When I got into the field, they didn't. It was kind of empiricism. You drew lines, you plotted graphs, and you said that roughly follows this line. Now we have these beautiful computational models, and they run on the biggest computers in the world, and they're able to calculate what would happen in a fusion device if we change this, if we change that. So we can start to do innovation in a virtual space, in the space of computer simulations. And what we've done at Princeton is we began to sort of systematize this using artificial intelligence and the world's biggest computers and these models, and looking for the optimum configurations and starting to look at new stellator configurations. These are these wonderful twisted magnetic field configurations. And some of our young people there on the top right is Elizabeth Paul, who's just become a professor at Columbia University, Matt Landerman, Felix Parra, who's our head of theory at Princeton. This guy on the left is Eggy Coleman, Noah Mandel in the middle, and Adele Wright on the bottom. She's just gone as a professor to Wisconsin. They're starting to say, what would be the optimum configuration in the computer? Could we build that? Could we make a better bottle for our fusion device? I think there's some really fantastic things going on in this space. And there are at least 3 of the spin-out companies are going along the line of taking these configurations and trying to make them and see if they will make a better fusion device. I think delivering electricity by 2035 is a bit of a stretch, to be honest. But it's a good goal to say, we're not just doing fusion for science, but we're doing fusion because we want to make some electricity. Thank you very much.
Thank you, Steve. I mean, we start seeing a pattern. I mean, almost all the 3 of you talked about this surge of also the private industries coming in, and this cross-fertilization also that you mentioned. This is something that seems to be accelerated now. So yeah, we'll talk about this more later. Let's now go to our next speaker, Piergiorgio Sonato, who is the president of RFX Consortium in Padova, Italy.
Thank you. Thank you very much for having invited me for this panel and with this colleague. In my contribution today, I want to witness what is the role of the Italian research and industrial environment is working for fusion. Also because I think that, as I would like to demonstrate and convince you that we are actually in Italy in a situation in which from the scientific point of view, technological development in the research institution and the technological transfer and involvement on the industries, we are in a situation today that is unprecedented in the history of the research on fusion in Italy. You see here in the background the CNR, the National Cancer Research Site in Padua, in which we host 3 of the 4 okay, there is some noise. Okay, probably it's better now. In which we host 3 of the main 4 facilities that are working or they are under construction and development in Italy. We see in the map or the cities in which we have research institutions that are working on fusion research. Now I start to introduce you the 4 main facilities in which we are working in Italy. The first one is, okay, we have already understood from our colleagues and from the video that the mainstream line for the development of fusion is on tokamak and the Stellarator. Stellarator, I think that HARTMUT later will speak something more about this. But in Padua, we are developing a different concept in which, if for the Stellarator we have in our toroidal plasma no plasma current and all the magnetic field is generated by external coils, in the center, in the tokamak, we have a large toroidal plasma current, as we have understood this morning, and we have a large toroidal field produced by external huge windings. In the reverse field pinch, in this line on the right side, we have large toroidal current, large poloidal current, and therefore most of the magnetic field necessary for the confinement of the plasma is generated by the plasma itself. From the external coils, we need only to generate some fields to control the surface of the plasma. And by controlling the symmetry of the plasma column, in the center of the plasma, there is a core that is very hot. It has an helical shape, similar to the helical shape that we experienced in the Stellarator, in a completely different confinement. From the physics point of view, this is something that is very interesting. And this development has been done in RFX, that is this toroidal experiment in Padua. The most important results have been obtained in the last decade, and now this experiment, that is one of this Italian infrastructure that is at high priority in the energy sector, now is under upgrade to try to explore new performances and better performances than before. This historically is the first important device that is still under operation today. And the second one is something that has been mentioned by Pietro a few minutes ago, the neutral beam test facility. In Padua, we have the only part of the ITER that has been built and has been decided after the decision to build the ITER, has been decided to also establish a facility for the development of one of the main heating system of ITER, the neutral beam test facility. This neutral beam test facility that is hosted in the premises of Padua, of the CNR, has been or is under development with the strong cooperation with 3 of the partners of ITER. Japan, that supplied the 1 megavolt power supply, India, and Europe through the Fusion for Energy Agency and with Eurofusion, therefore with all the European laboratories that are working on the development of fusion in Europe. And within this facility, that for one side replicate exactly the neutral beam that will be installed later and reproduced into system in Cadarache, we have two facilities. One is SPIDER. SPIDER is a source of plasma to generate negative ion of hydrogen. It is easy to remove one electron from hydrogen. Hydrogen has only one electron, but it is difficult to attach a second electron to the hydrogen species. We need to do this because when we accelerate at 1 megavolt one negative ion of hydrogen, it is still possible to remove this electron. If it is a positive ion, it is not possible to reattach the electron, and therefore the beam needs to be neutral to be injected inside the plasma. SPIDER is devoted to this experiment, is in operation, has operated 3 years and a half, and now is on the final reinstallation after a significant refurbishment of the source. Mythica is the full power and full energy injector that is under development for ITER. This injector, we can, please, if you can launch the video. In a radio frequency plasma source, we generate ions and we generate radicals. These ions of hydrogen will be converted in negative ions, and then they will be extracted by an electrostatic field that will accelerate the beam and will extract the 1 megavolt beam. We have 1,280 beamlet that produce negative ions. Then, after the generation of this beam, the beam must be neutralized, and only after the neutralization we can inject inside the plasma. Now, here we see the source of SPIDER, and on the bottom left we see not the movie of the beamlet that are accelerated, but the real video or the real camera picture of the beamlet that are extracted and accelerated in the bottom left. On the right side, you can see and observe some relevant components of Mythica, the vacuum vessel, the transmission line. We have in the transmission line 1 megavolt of voltage between the inner conductor and the blue body that you see on the top right side, with the flag of Japan that has built this power supply and this transmission line. You see also the inner of the transmission line, where in the internal, in the conductor in the middle, here we have 1 megavolt. On the surrounding vessel surface, we have 0 volt. 1 megavolt in less than 1 meter. It is something that is incredible in insulated gas. And another component. The fourth facility under construction in Italy is the Verter Test Tokamak. Is a unique facility in which we want to develop the system that has to handle the power and the particle that the reactor will produce, that must be extracted from the plasma. This is a device that is under construction in Frascati, in the Enea site, in which collaborate a number of institutions that is also part of the institution of the consortium RFX and also from Eurofusion. But the last part that I wanted to mention to you is that all this activity for the construction, the installation, the integration, and the commissioning and operation of the facility in Italy, and the collaboration that the research institution have with Europe and worldwide, have also produced a transfer technology to the industries. And I show here only the relevant cooperation for ITER. You see that vacuum vessel, half of the vacuum vessel more or less is built by Italian industry, top right side. Half of the toroidal coils are produced in Italy, also close to Padua and close to Venice. The component, mechanical and heat flash component are produced also in Italy, and also the superconducting coil and to superconducting strands within the coil is the technology developed in Italy. But not only here. Here I show only superconducting and mechanical, but also on power supply system, in control system, in diagnostics and in integration. The Italian companies, there are, as I mentioned before, tens of companies that have collaborated or are collaborating with the research institution, and the technology transfer is very relevant in the Italian environment. Thank you very much. I'm sorry if I've been a little bit long, but...
Really nice to see also that Italy is at the top of this technology, together with many, many other partners. Okay, we move on to now HARTMUT's ZOHM. And HARTMUT, he's not only, the director of the Max Planck Institute for Plasma Physics, but he's also a very famous, and I see some of you smiling, a very famous TV star, because he's running this YouTube channel, and he says he has 300,000 followers in this YouTube channel. So go ahead, please, HARTMUT.
Thank you. Okay, so we are a bit late, and I was told to keep it simple, so that's what I tried to do.
You have 10 minutes.
Relax. I have only 4 slides, and they don't have a lot of text, so we should be great to go. So the first thing, and it has been mentioned quite a bit, I want to point out is the aspect of international collaboration. Pietro said that one of the 7 partners of ITER is Europe. But in fact, Europe is not one country. So I think it's a major achievement in the European Fusion Program to get our act together and to be organized across all of Europe. And we do this in a so-called consortium. So we are financed, co-financed by the European Commission. And we are co-financed as a consortium out of 29 countries, which has 31 research institutions. And you read yourself, a lot of people involved, universities. We have access via the universities to students at very high level, and all in all is about 4,000 persons working in this. And the way this is done in this consortium is that we get our act together literally by preparing a proposal to the European Commission how we want to do the research on fusion, which brings us forward in an organized way. And we bring this to the European Commission, and we are financed as a whole, and then we distribute within this consortium. So you can see all the European Union countries in there. You see on top Switzerland and the UK, who are not part of the European Union, but they have or had access to the Euratom program over which we are financed, and we actually have a very good collaboration with them as well. So Switzerland is more or less still a partner in there. The UK, you all know, is even no longer Europe in some sense, but we still work together with them very well. And so you can see this, and the way this works is that if we have a physics challenge, like ITER comes and says, we want to know X, Y, Z, how does the plasma operate with this? They ask actually Eurofusion, and the Eurofusion consortium says, let's discuss which of the machines or which of the laboratories, the yellow dots in this, is best suited to do this. And then it is transferred to these, and we work all together on this problem on the one machine which might be the best suited, or even 2 or 3 machines. These are tokamaks and stellarator, and we could figure out things much better if it was just one partner who was paid or, say, being tasked to do this. So I think this is a great achievement within Europe. We're very proud of this, and I think it also works quite well. We do have a roadmap to fusion electricity, like the one that Steve was discussing. You note we don't have numbers in terms of years here, so you can ask me later about it. But what you see is On the upper branch of this, these are all the experiments, the experimental devices which we are using in order to understand how to make the plasma hot, how to do these 250 million degree plasma, and how to keep it burning or say in this state for a long time, which used to be seconds only, as you saw, which is now tens of seconds, as we have seen in the Japanese tokamak, could be up to hundreds of seconds. And then this is the culmination of this will be ITER, where we can really produce power with it. On the lower leg of this, the blue arrow, you see all the technology. It was already mentioned, the more you go into doing this towards commercial fusion, where things should not be done by physicists who put tape around stuff in order to fix it, but who really want to build something that you can run for a very long time, you have to do all this engineering here. And so there is all this engineering. It doesn't really matter what the individual dots show, but it's very important that these things, so the plasma physics via ITER, the technology via ITER, but also this dedicated technology program go into something we call DEMO, which is a demonstration fusion power plant. And you can see the aspect in this version of the roadmap already that Steve has mentioned. It is a parallelization. If you are in publicly financed research environment, usually you don't go in parallel. You don't say, let's try this, let's try this, let's try that, and only one of them will work, or maybe none of them. So we waste the taxpayers' money in some sense. If you have more partners and private money flowing into the program, which is the case now, you can actually go in parallel and say there is more risk appetite in industry, and they can fail, and failure is part on the way. Just look at what SpaceX, how many rockets SpaceX exploded before the first one took off. So this is something we anticipate. So the demonstration fusion power plant is actually running in parallel, taking all the information from the experiment, from the ITER in the end, which is very important in terms of the plasma physics demonstration, and also the technology, and leading into the fusion power plant, which you see on the right side. Now there is another thing which is special about Europe. You see there are two power plants, which means we haven't made up our mind, if you like. There is one, the upper one, which is the tokamak that everybody was talking about. And the lower one is what we call the stellarator, in which you have seen in several instances in the video and others as well. So Eurofusion says, let's go for a tokamak demo, but let's also strengthen the path on the stellarator research. And maybe the stellarator in the end is the better power plant if you go to this. And I'm also saying this because in Germany, we think the stellarator is great. Now I'm coming to the German part of the program. And so, whoops. And this machine you have seen quite a bit in the slides now. It's called Wendelstein 7X W7X. It's a stellarator. I'll come back to this in a moment. It is run in Germany. It's the world's largest stellarator. And it has been commissioned in 2016 and is now running for 6-7 years and produces very nice results. It's the largest machine of its kind. It has broken many records, world records for the stellarator, and yet we are increasing this and sort of doing more experiments. So what you see in the middle is a computer animation. You see the plasma is this yellow thing which winds around. If you follow the green line very well, you will see that it winds around such as has been described for the tokamak itself, but this is done by twisted coils, which are all on the outside of the vessel, so there is no current in the plasma different from the tokamak, which means this machine is intrinsically steady state. So you turn on the magnetic field, superconducting coils, by the way, on W7X, and then you can run it for as long as you like. And as much as physicists like self-organization, PIERGIORGIO, I think for an engineer, self-organization is terrible because the plasma might go where it wants. So we really want to go for sort of the thing which is most bound to the external control of the magnetic field. So as I said, this machine is run in Germany near the Baltic Sea in Greifswald. And you see some pictures of the assembly here. It's a huge beast, actually. It took a very long time to build this up. So it's 10 meters. It's 10 meters from the left to the right. It is superconducting coils in there, and it went into operation very smoothly. So in fact, there was not too much screw up in this on the way. We had our problems as well, and it's now running very well, actually. And this brings me to the last slide being what does the German program look like? The German program, as you can imagine, the direct funding for this research goes into a few large centers because this is big research. I mean, we have the W7X, the Wendelstein stellarator, which is run in the north. So up there, if you're familiar with the German map, Greifswald is up there where the sign of Max Planck Society is. This is Greifswald, and it's about 500 people working there. And so this is a large, like a national lab, which is run and mainly financed by the government, but it has to be concentrated in this. We have another one, branch of this Max Planck Institute, where I'm working in Garching near Munich. So there we have a machine which looks prototypical of what ITER looks like, and we do a lot of research which is directly related to the support of ITER. And then there is the more technology-oriented research. So there is Jülich, where you see the big J, which is an institute of the Helmholtz Association. There it's mainly studied plasma wall interactions and materials, which are very important. I mean, the plasma somehow has to touch the wall, and then you have to get rid of the power which goes there. And there is the specific fusion technology, which is done by another Helmholtz Association institute, which is the KIT Karlsruhe Institute for Technology. And to finish with, we also see startups in Germany, which is a great thing because there's additional money coming into the game. So we have 2 recently founded startups in magnetic fusion, Gauss fusion and Proxima fusion. No surprise, they look at the stellarator because they are located in Germany, so they find this a very interesting concept actually. And there are also in inertial fusion, I should say, startups. What this has prompted is that we also see more money in Germany being put into fusion. So the government, the BMBF, Bundesministerium für Bildung und Forschung, recently announced another 370 million euros which go into fusion for the next 5 years. And this, to some degree, has been prompted by the successes that Steve has mentioned, but also by the feeling that now is the time to involve industry with the startups, for example, and to build up a fusion industry ecosystem which could, in the end, deliver the final fusion reactor for this. Because this, the fusion power plant itself, will not be built by research institutes. This will be built by industry. And I think I more or less kept my time and stopped. Thank you.
Thank you. Wow, you guys have been perfect. Thank you so much. And again, thank you for coming here. I mean, Steve comes from the US, Masaya comes from Japan, Pietro comes from France, maybe, or wherever you were. He's already always traveling around. So now we leave, this remaining time for questions to you, starting from you. And please, if you want to ask a question, wait for the microphone to come. Since we are streaming this event. So let's start here, and here's the microphone that comes. You can ask your question to any of the speakers or a specific speaker. You go ahead, whoever you want.
Thank you very much. So first of all, thank you to the Italian Embassy to assembling such an impressive panel. I'm very, very glad to have the opportunity to listen to you. I was really happy about what Steve mentioned regarding the progresses in simulation, because as I remember, MHD simulation belongs to the most nasty things that you can do as a physicist. Can you expand a little bit on this process, especially with regard to the question, could it be possible that when these simulations get more and more accurate and powerful, to tackle the challenge of the sheer size of these machines? I mean, obviously we have some scaling issues here, but one of the most pressing critique points regarding fusion activities for plants is the investment size, the sheer size, the complexity. So if there is sufficient progress in simulations, would there be a possibility to build more compact machines?
So, sorry.
Yes, go ahead. Go ahead,
yeah.
Steve. Yes.
I mean, this is really the motivation behind the big simulation program, which is try and push down the cost and scale of fusion to make it more market ready in terms of its size. What dominates most of our devices is that the heat leaks through the magnetic field through turbulence. Tiny little swirls, because it's hot in the middle and it's cold at the edge, these tiny little swirls carry hot stuff out and cold stuff in, very much like when you heat a pan of water on the gas stove. The bottom is hot and it rises, and the top is cold and it falls, and you get bubbling in there. And What we've learnt to do is to minimize that turbulence, but not get it out of there, right? There's always some turbulence inside the plasma. And about 20 years ago, we first started simulating that turbulence with some veracity because the plasma is very thin, so it doesn't really behave like a fluid. It behaves like a collection of charged particles. And those charged particles are going around the magnetic field lines very, very fast compared to this turbulence. And so they behave like charged rings because they're going around almost in circles. And we have something called gyrokinetic simulation. That 20 years ago was very, very basic. But now there are codes, and there's codes at Munich, and there's codes at Princeton, that actually can simulate that turbulence almost fast enough that you could do it between a shot on the experiment. They still use very big computers, and there's a lot of mathematics that goes into it. But the early career people are really advancing this extraordinarily fast, and then integrating that with AI tools, or artificial intelligence tools, that will allow you to take bigger steps in your calculations. What we've actually done is, what my last slide was about, was to actually have a sort of optimization routine looking for better and better configurations that have less and less turbulent transport inside them. We can actually go through a loop and iterate, and then if that configuration isn't quite good enough, we tweak it and we go to another one and we go to another one. That wasn't possible 3 years ago. And actually, the German stellarator was designed in a very similar way, but before we could calculate the turbulence. And so now, by integrating the turbulence, we've got real veracity to the model of the plasma that I think we can really use to drive down the cost and scale of fusion.
Thank you. Thank you very much. I think there's another question first here and then there. Yes, please.
Hello, good morning. My name is Jürgen Mlinek. I was running the Helmholtz Association as president for 10 years and was in charge somehow also for nuclear energy and nuclear fusion. First of all, let me thank the Italian embassy again for being part of the Berlin Science Week and bringing together here to Berlin such a panel. Welcome to Berlin, by the way. So when I was a young student and I had to give a seminar talk on nuclear fusion, the message was nuclear fusion will be 35, 40 years ahead. You know, this is the so-called fusion constant. When you talk to people today, it's always, you know, not tomorrow, it's some decades ahead. So maybe you can say a few words also on realistic timescales to get fusion for electricity. I think this was a very important remark by you, Steve, because fusion for science is one thing, but fusion for electricity is completely different. It's a completely different, I would say, also mental setting. And I guess many of you have seen this movie Oppenheimer, you know. There was a need for urgency to come up with something really big. Maybe there is more urgency now also for fusion. But, I mean, let's be realistic. You said that too. Is this urgency really in the heads of all those who not only working on it, but have to support it, politics and also society? So, final remark, what about Russia, China, Korea, South Korea? How are they doing in this worldwide competition? Maybe we should also get a few of the insights that you have, how, I mean, the competitors, you know, outside the Western Hemisphere are doing.
Yeah, maybe this could be something that you could comment on to start with, and maybe others could add. Pietro, please, start.
Yes, so, your last question, presumably.
Yeah, that was a question.
Yes, my observation is that, first of all, Russia and Korea and South Korea are collaborating in the ITER framework, making ITER really their centerpiece, particularly for Russia, because there is really no other big research infrastructure in the Russian Federation for what concerns fusion. Although the name tokamak comes from researchers in Russia, they really made ITER as the centerpiece. And in Korea, they have a research infrastructure called K-STAR, which is a relatively small size superconducting tokamak. But they are, in essence, strongly counting on the ITER project. In China, there has been, in my observation, an impressive acceleration in fusion research in the last couple of decades. And what I could see recently is something which is really impressive. So they are investing a lot in developing technologies. They are supporting the ITER project very strongly, I must say. But at the same time, they are developing a parallel research infrastructure, which are, say, quite large. So as my colleague MASAYA GT60SA now is the biggest tokamak in the world that just started operating. My expectation is that we will see burning plasma experiments being developed also in China. So that is, I think, quite encouraging. If I may spend a few more words about
many questions on this.
About fusion. I myself, when I started working, I asked the question to my boss, and my boss told me, "You will operate the demo." And evidently, this is not going to happen. And so, but
maybe somebody in this room will.
Maybe. But I won't tell them. I won't tell them that. So I think I totally agree on the fact that modeling will be central to the development of fusion. Because we know that fusion is possible. We know that. And we also know that we can get more energy out than the one we put in. We know that physically this has been demonstrated. We don't know yet if we can sustain this process for time constants which are, say, in the minutes or hours scale. From a few seconds to minutes and hours, there's a big difference because the time constants of structures is changing and everything is driven by something which is called power density. Fusion is something which is specific. It needs to operate at 150 million degrees. This means, and sorry, I think like an engineer because I am one, you cannot really exhaust the power by embedding a matrix of coolant inside. You have to get the power out in order to run, say, steam in a turbine. And you cannot really do this in fusion other than on the surface. You can do this with fire. You can embed the fire in a heat sink. You can do this with fission. You can embed the fuel cells in the water, but you cannot do this with fusion. You have to get the power on the surface. And you need the big fireball because as we know, we cannot sort of get the condition on small scale. A lot of it is driven by power density. So I believe that, personally, that the development in modeling will not so much reduce the size. I don't think so. Because size will not make it economical. We need hundreds of megawatts. We spoke about megajoule before, and megajoule, as Steve said, is a candy bar. We have, in ITER, we will go in terms of compare with jet. Each pulse will generate 10,000 to 100,000 more in terms of energy. It's a huge step. So this is what is in facing us. We have now that we know that we can get more energy out than the one we put in, the question will be, can we do this for minutes and hours? That will be the scope of ITER. And then the question will be, can we get more money out of the money we put in? This is a key question, because for an energy source to be on the grid, it's one thing to put it on the grid just for sake of it, and it's another thing to put it on the grid so that utilities will buy it. And for that, I think essentially the computer modeling will allow to reduce complexity. Cost is not just driven by size. Cost is driven by complexity. And I believe that a lot of the complexity that you see in ITER, that we have to face in ITER, will gradually get much, much simpler by finding better magnetic configuration and being able to optimize the structure in a way that will make it much cheaper to build. Thank you.
Thank you very much, Pietro. I see that HARTMUT wants to add something here.
Yes, I would like to address the fusion constant, because that's really one of my favorites. I was actually surprised it was only the second question. Usually it's the first one. So first of all, I think when I heard it the first time, it was 50 years, and then it was 30 years, and I think now we are saying 20 years, but you can always say 20 years. I think this is the first time in my career that I see a sense of urgency coming on for fusion, which we haven't had before. So in Germany, where there was usually, we were always doing basic research in fusion, now there is this push by the BMBF. I think this is also because we see the chance to parallelize, as I said before. The sense of urgency comes from several. I think it's a bit embarrassing. I found in Germany there was more sense of urgency when people were told that they couldn't heat their houses in the winter than when climate change was always on the plate. But for whatever reason, I think there is a sense of urgency. And this is a chance. So what we put forward as an estimate was what we call the 2020 strategy, which is 20 years, 20 billion euros. And I think this is more or less consistent with what the other partners have said. But it's very important you get the 20 billion euros, at least on the horizon, to do this, because just saying we'd go faster without having the measure to do is very difficult. And the second thing, you have to accept that we can go in parallel, and we can go down a path which might fail. We have to use the large increase in money to parallelize and to do things which might fail at some point. And I agree with Steve, some of the things we see of the private companies look very challenging if you're generous, and maybe they will never work. But on the other hand, we will learn from all of these. And doing this in parallel is a luxury which we haven't had in the program. You know yourself how long we took to say, we can do the next step, because we have shown to 99% we are sure. So I think now is the time, and I'm just hoping we can channel this in a direction where we really go faster. And then maybe at some point it goes to 10 and then to 0 years, who knows.
Thank you, Hartmut. Yes, Steve wants to add something.
I just want to...
please use the microphone.
Yep. I just want to make... is this on? Yep. Okay. Sorry. There are young people in the audience. And I do think that sometimes we think, my generation thinks we've had all the ideas and now we need to just work them out. There's probably some really smart things that we don't know yet, and that another generation of scientists and engineers coming into fusion will discover. So don't listen to people like me. Think for yourself. Fusion needs many more ideas, and I think the challenge is not doing fusion. It's doing fusion at a cost the consumer wants to pay for their electricity. And if we can do that, we'll never not know how to do fusion.
Yeah. Thank you. Thank you, Steve. So I would like to now give the microphone to, yes, the lady in red.
Thank you. Hello, everybody. I'm Marta. I'm from University of Oxford, and I worked at TAE Technologies. And what I was very, well, maybe not shocked by, but saddened by, is that Marvel Fusion decided to leave Germany and invest in the US. And I was researching the landscape of various European countries and seeing that a lot of them are still focused on ITER, but with all the confusing and controversial timelines and mismanagement and certain logistical issues. I think the EU should focus a bit more on supporting the private network of various fusion companies, like the UK does. And what I would find interesting with regards to that is I've been looking at fusion legislation, and I know that the EU is, I see that there is a sort of like start that people are becoming more interested in fusion, but there is still, no legislation on the table perhaps. But I would be interested to know, how do you think fusion should be legislated? Should there be legislation that is fusion specific? That I see that a lot of it is ITER focused. I wouldn't want to see something that's just a copy paste of nuclear fission legislation, and I don't think it should be the same legislation that would be for renewables. So where do we find this niche for fusion legislation and all of that?
Okay, so who wants to take this? Yeah, there you go. This is a tough one.
Well, first of all, the company Marvel Fusion didn't leave Germany. They have a project where in the US a lab Colorado Boulder University is paid and they do experiments. I think that they are still here in Germany, so this was maybe a bit exaggerated in the press. But this is not, I think the real answer, so the real question you want to have answered is about the legislation. Yes, so ITER was, the regulation of ITER went under the French law, and since there was nothing comparable, it went via fission. So this is the first thing to do would be to say we have something which is strict, which is about fission power plants, and we will go and see if we can make life easier, because fusion doesn't have the same risk of accidents, doesn't have the same class of high-level waste, which takes very long time. And what we see now in the US, and the UK is furthest advanced already, is that they do it the other way around. They come from what they call legislation for accelerators. So it is a source of radiation, and it has a nuclear aspect for sure, but it is very different from fission. And so the present strategy is in the US and the UK and also Japan to start from this and say this is very different because we have different accident scenarios which are not by large, and also waste which is by large different from what is being has in fact already been seen in fission, and let's build up from this. And we are trying to make this work in Europe as well, now continental Europe, because the UK already went ahead, and say we should do the same thing. We should start with something actually like W7X and Astex upgrade. Our German experiments are regulated, they are regulated under a very different Strahlenschutzverordnung than they are a fission power plant, and we should keep this. And we should start and then say, let's see what we have. And we will have to add stuff because it produces so much more radioactivity, but it is not like a fission power plant. And I think you see a push everywhere. I mean, each of the companies has in big letters on their website, we need a legislation, we need rules, and we need them now. And this is also a very important aspect. I just come back last week from Boston, from CFS, this startup, visited them. They actually say we need the safety, the security to know that if we start now building a power plant, we can also operate it. And they actually said we're willing to go to the UK if the US doesn't come and say we will have our rules and the UK has rules. So it's clear that if you want to go fast, you need these rules. And so there is a big push for this also in Germany. If you read the BMBF Bericht for the strategy, it's already featured in there.
Thank you very much, HARTMUT. So, let's see, are there other questions? There's one. Sorry, yes, PIERGIORGIO, go ahead, please.
Add something related to the regulation. It is clear that when we wanted to build in our house an electrical plant, or we wanted to use any appliance or apparatus, this must follow some rules and regulations that are established by regulatory bodies. But all the path or the trajectory to arrive to the regulation is a quite long process that develops with the development of technology. This is valid for any kind of technology, for electrical plant, for pressure vessel, for any kind of our activities. We need to follow regulations and rules that are established by bodies that are in charge to develop this type of rules and regulation. Fusion cannot escape from this, has to follow the same. And the time to develop the regulation for which, when we are able to produce electrical energy, we can switch on and inject electric energy in the network, in the grid. What are the rules for the design, for the construction, for the test, for the acceptance, for the assembly, for the integration, for the commissioning, before to be able to switch on the power plant? This is something that is a process that I am a poor engineer like Pietro, some electrotechnical engineers. But all these trajectory, all this path is something that took a very long time to be developed. And there must be a step of test and of verification before to adopt this. This is a process that we cannot skip for any kind of type of technology development, not only fusion. This is clear now. And the ITER for this will play a very important role because it's the first of kind of fusion plant, fusion experiment that will address also most of the part of this part of the process. But there are others. The material, HANADA mentioned in Roccascio the development of a facility for materials. This is another aspect. The divertor test tokamak in Italy will address another aspect. Then there is the problem of the fertilization, production of tritium from lithium. This is another aspect that is to be developed. But on top of that, there are the problem of definition of the regulations. And this is, from the engineering point of view, is something that cannot be developed in months or a small number of years. It's something that requires long time of development from all the regulatory bodies.
Yeah. Thank you. Just maybe we have time for a last very quick question, a very quick answer. Come on. Give him the microphone.
Can I ask a yes/no question?
Yes, go ahead.
So for everybody, was it harder to go to the moon or is fusion harder?
So let's see.
That's not a yes question. I think evidently from my standpoint it's...
Oh, sorry.
Evidently, it is harder to get fusion. We have to, on the other hand, think that because getting on the moon was done in a different time, of course. So it was very hard to do it then. I believe that in today's money, that project would cost 200 billion. So it is several times ITER, although ITER is very expensive. We don't deny that. It's a major investment, but it was done at a different time. I think they are both equally, if I may say, so it's neither yes or no, they are both equally tremendous challenge from a scientific standpoint. I don't think that it's just energy. I think it's also, yes, to achieve a new frontier. There are a lot of, say, spin-offs. Going to the moon had its own purpose. So I believe that there are similarities to that. But if I look forward, certainly from the standpoint of today's technology, it remains very easy now to go to the moon. It remains very, very complicated to achieve fusion and to make it, say, economical.
Thank you. Thank you very much. I think, unfortunately, we have to close this event here. But I thank all of you for attending, and I would like to again thank our 5 speakers. Thank you so much.